Hello students of Seneca, this is Jono. Thank you for joining me on this chemistry A-level revision episode. And in this episode, we are going to the Maxwell-Boltzmann distribution of energies. Hey! Okay, so let's dive in. What is this elusive Maxwell-Boltzmann distribution? Well, basically, it's a handy little graph that shows the energy distribution of all the molecules in a gas. So it's a graph. And the number of molecules is on the y-axis, and the kinetic energy of the molecules is on the x-axis. The origin is 0, 0, and no molecules have zero energy, so the curve passes through the origin. Important point to remember, especially if you need to plot the graph. What is the peak? Well, there's a peak in the middle, and this represents the most likely energy of any molecule. There are more molecules with this energy than any other energy, so that's what the peak shows. The area under the graph. The area under the graph gives the total number of molecules. You can think of this as like adding up the number of molecules with every particular energy. Molecule energies. The average energy is to the right of the maximum peak. The tail of the graph is asymptotic to the x-axis. It's a hard word to say. And asymptotic basically means it's like it's going to get closer and closer and closer to that x-axis, but honey, they're never going to touch. Like, they're never going to be a thing. They're just not very compatible, whatever. It's not a big deal. We don't want to talk about it. But that tail is asymptotic to the x-axis, so it never quite touches it. So it tends to 0, but never quite touches the x-axis. And this reflects the fact that there is a small possibility of having a very high energy molecule. Activation energies. We can mark the activation energy on the Maxwell-Boltzmann distribution. This allows us to view the number of molecules with the energy to react. On the left-hand side of the activation energy mark, molecules have less energy than the activation energy, so they can't react. They're just chilling. They're just happy to be there. On the right-hand side, molecules have more energy than the activation energy, and so they can react. They're good to go. Remember, why does the Maxwell-Boltzmann distribution pass through the origin? It's because no molecules can have zero energy, and the origin is 0, 0 on a graph. The peak on the Maxwell-Boltzmann distribution, do you remember what that represents? Is it the total number of molecules? No, it's not. It's the energy that the highest number of molecules have. So that's what the peak represents on a Maxwell-Boltzmann distribution. Now, it's really important to know the effect of heat on the Maxwell-Boltzmann distribution. If we remember, the area under the graph tells us the number of molecules. Heating can't increase the area under the graph. We can only do that by adding new molecules. But heating does increase the average energy of the molecules. So heating the reaction moves the maximum, so the peak of the graph moves to the right. However, it also lowers the number of particles with that energy. So heat on the Maxwell-Boltzmann distribution. Damn, that is a hard word to say sometimes. X and a Z in the same little word. Honey, it's a lot. Effect of heat on the Maxwell-Boltzmann distribution. That peak, it is going to be lower and it's going to shift to the right. Two really important factors to remember, and that's going to be all over the mark scheme for a Maxwell-Boltzmann distribution question. The peak shifts to the right and it's lower. It shifts to the right because the molecules have higher energy, but the peak is lower because there are less molecules with that peak energy. Two really important facts to remember. If you take away anything, take away that, but hopefully you'll take away a little bit more. So if we raise the temperature, the curve on the Maxwell-Boltzmann distribution, does it have the same area? Yes, it does. Is the peak higher? No, the peak is shorter, but it lies further to the right. Remember those three facts. So, effective temperature. As the temperature increases, the peak is going to shift to the right and it's going to be lower. I know I've been saying that a lot, but sometimes you have to go over things like 3 times before they even stick. I think my chemistry teacher taught me that when I was doing A-levels, and it's good advice. So there's no harm in going over things more than once. It helps them consolidate. So activation energy. The Maxwell-Boltzmann graph can show us where the activation energy lies with respect to the energy distribution of all the molecules. We can mark onto the distribution line showing where the activation energy lies. And the line that we add for activation energy is always vertical. And this is because the x-axis represents energy, so a vertical line will mark a specific energy. On the left of that energy mark, molecules have energy below the activation energy, and on the right-hand side of that mark, molecules have greater energy than the activation energy. Okay, that brings us to the end of this episode. That was a lot to take in, so I hope your brains are feeling all right. I would maybe consolidate this by having a go at sketching some of your own Boltzmann distribution graphs. Try and do it from memory. Active recall is the best way to try and consolidate things. And I hope you remember the effect of increasing the temperature on the Maxwell-Boltzmann distribution. Remember, the area stays under the same. We don't change. The area under the graph stays the same because we can't change the amount of molecules by increasing the temperature. But the molecules have high energy, so our peak shifts to the right. But there are less molecules with that high energy, so our peak is a little bit lower. If you remember those three things, my work here is done. Thank you for joining me on this revision episode, and I look forward to catching you in the next one. Thanks.